All right, now what we need to do is specify the boundary conditions for our simulation. So SimScale has a lot of different types of boundary conditions available, all the ones you'd probably want for a basic heat transfer simulation. So you can specify fixed temperature values on outer surfaces. You can fix surface heat flux on any particular surface. You can apply a convective heat transfer coefficient, so that's what it means by convective heat flux, on the outside of any particular surface. And you can do distributions of those. So like if I have a surface, I don't have to have just one heat transfer coefficient across a surface. I can specify a spatial distribution of that, and I'm going to show you how to do that in a second. And then it also, although it's not really a boundary condition, it allows you to it allows you to specify volumetric heat generation in certain regions using the volumetric heat flux toggle. So in that, for that thing, you either have to have a like you basically need to have a salt, like you need to apply it to essentially an entire solid body, or a geometric, what's called a geometric primitive. I think I'll talk about geometric primitives separately. Here, I don't actually want to do that. Let's delete that for a sec. So the one thing you won't see in here is an adiabatic condition, which is also quite common. There's, well, two reasons for that. One is that you could just say that that means that the surface heat flux is equal to 0, so you could specify that. But in fact, for a finite element simulation, you don't have to specify that. The natural boundary condition for finite element method is the adiabatic condition. So if you go through this process of setting up boundary conditions and just don't set a boundary condition for any of, like for some particular surface, it will by default assign an adiabatic condition to that surface. That's can be convenient if that was your intention, but keep in mind that that means that if you forget to assign a boundary condition somewhere where you were supposed to, it will assign an adiabatic condition to that surface. So just keep that in mind. But most of the time that can save you time because you don't have to set up that boundary condition. All right, so what are we going to do here? So what I wanted to do was set up some convection heat transfer coefficients on some of these surfaces. So for all of these surfaces can be, so if I have flow going from left to right here, all of these surfaces are essentially flat plates that flow goes by. And so what I'm going to do is I'm going to borrow some of what we know from, I'm going to use a convection heat transfer coefficient correlations to assign the spatial distribution of heat transfer coefficient on these outer surfaces. So basically all of these surfaces that I've highlighted here can be thought of as flat plates. So basically just select them. And in this case, I'm not going to just assign a single heat transfer coefficient. You can, if you just like want to assign an average heat transfer coefficient on these surfaces, you can, but you can do better than that. You can actually specify the spatial distribution of the heat transfer coefficient using a formula. So before I started this video, I worked out that at least in SI units for this situation, for air flowing at a speed of, let's say, 3.5 meters a second, the corresponding heat transfer coefficient is 10 divided by the square root of the distance from the leading edge to the square root. So 10 divided by the distance, so that's x, from the leading edge to the square root power, 0.5. It turns out actually that our leading edge does not begin at x equals 0. We could have measured, here, actually let's do that. So I'll apply this temporarily and I'll come back and fix it. You can actually, let's say if I apply a geometric primitive, I can try to set up a point here to figure out where the leading edge is. Let's see, how did I do that? So where's my geometric point? Oh yeah, I can click, right? Pick from viewer. I want this point right here. So it says that that point is at, 3.575 millimeters basically. So let's call that 3.5, I guess. So I'm going to, when I set up my convective heat transfer coefficient, I'm actually going to offset the value here so that it starts at 3.5 millimeters, so that this becomes the distance from the leading edge to the square, and then take the square root of that, multiply by 10. I think I worked out that like that means that if you're in the middle of this fin where it's maybe an inch in, that corresponds to like a heat transfer coefficient of like 60. But anyway, so this is the formula I'll use to assign that. I could do something similar for these surfaces, which are also flat plates, but I can kind of see that these aren't the majority of the surface area here, so I'm not actually going to worry too much about assigning those. I suppose I could. It's a little complicated to assign this one because it's like at an angle, but I could. Oops, I don't want to assign that one to this. Okay, anyway, I'm not going to do that. Let's see, what else we got? So we don't have any surfaces here that have a fixed surface heat flux because we are going to model our heaters as volumetric heaters. Let's see, we already did this. We don't have any fixed temperature values in this problem. But if we wanted to do that, we could create a fixed temperature condition and then just like select the surface that we want. So the only other thing we have to set up are these volumetric heating locations. So I actually have two different ones. So I have this front heater that I wanted to correspond to a total amount of heat generated of 20 watts. But now this is supposed to be in units of watts per meter cubed, because it's a volumetric heat generation. So what I need to do is a little bit of side math to figure out what that value is. So I'm going to just pull up my Python window here. So what I was trying to do is 20 watts in a space that was 19 millimeters squared by, that cube was supposed to have a height of 2.54 millimeters high. So that corresponds to some gargantuan number. So looks like it's about, let's call it 22 or 21. It looks like it's 22 e to the 6, something like that. 22 e to the 6 watts per meter cubed. And it's a gigantic number because this is in meters cubed. Anyway, that'll do though. That's what we're looking for. So that's our 20 watt heater. I'll give it a suggestive name so that I can remember what it is. That's our 20 watt heater. And then there's a 35 watt heater on the back side. So that was supposed to be this heater. And if I do the same math for that one, that's supposed to be, looks like 38 e to the 6. So it's a big number. So make sure you get that number right, because if you don't, you're going to get really tiny temperatures when you go to do this. Okay, and I think that's actually the only conditions we have. Let me rename this so that this is a 35 watt heater. This is best practices here. And I will rename this to be our fins. Fins/flat plates. And this is for a 3.5 meter per second oncoming flow. That's what I calculated that heat transfer coefficient for. Okay, so